Recording first. Okay. Okay. So what we are about to see today is one effect that I mentioned briefly that there are so many applications in today's technology. Actually, this technology has been like here for a long, long time, and it has been integrated to your everyday lives so much that some of you might not even notice that you are using it. All right. So this is the Doppler effect. And the key idea about this one is, so if you look at the slide right now, you can see that you have a source. For example, maybe there's a uh, the car, maybe just like honk, there's a sound coming out from the car. It could be the engine, it could be the siren, it could be horn sound, whatever. All right. And there is an observer, and the observer is right now moving. So this one give you some complications of the observed frequency. And you have heard of this one, like every time that there may be like an ambulance passing you by, and then you hear the sound of the sirens changing the pitch. That is the Doppler effect. Okay. Or you have like a super fast like motorcycle, or you watching like an F1 broadcast, and then there is like cars or there's motorcycle just zooming in and zooming away from you. It's like, I think that's the easiest way to mimic that sound. So on the way that the incoming car or the motorcycle coming to you, you can see the pitch is going up. It's like, and once it's going away from you, it's like, so it's like, something like that. That's kind of, I don't know. That I think you know what it's doing, right? All right, cool. So that's what the Doppler effect is. So it's the change of the frequency due to the movement of, in this particular example, was the source that is moving. However, on the other hand, if you also travel, the frequency that you observe will change as well. So right now, what we are dealing with is there are two sides of things that can change your observed frequency. It's either the source moving, or it's either the observer moving, or even better, both of them could be moving at the same time. So the key calculations that we are trying to get to is what can, or how can we calculate the observed frequency. Okay, sounds like a good things to do. That's the goal. That's our sort of like the main points to attack for this particular topic right here, is to calculate the observed frequency. All right. And then we're going to spend the first hour talking about this one, and then you're going to master this one. It's going to be simple. I hope at the end, I'll try to make it simple enough. All right. So let's take a look at the setup. What do we have? All right. And before starting the lecture, we had some discussion about this Doppler effect right away. And it's, if that helps you, it's right here. So think about this one. The car, okay, could be moving. So this is a source that's generating the sound. So in this particular figure over here, the car is stationary. So as you can see, the sound waves are propagating out. They are sort of like drawing it in terms of like you have a even spacing. So you can think of this one is that each cycle of wave is just getting, getting expanded. So it's getting bigger and bigger and bigger and bigger. So you can consider that this particular, from one cycle to another cycle, that's can be written in terms of this, that's equivalent to one cycle. Think of it that way. All right. But it could be anything. You just try to draw like it's called a wave front. Okay. And then you have another wavelength coming in and then a wavelength coming in. So that's an idea. All right. The driver attempt. All right. So now the thing is, the observer is trying to, right now is approaching the car. Okay. So my question is, what should happen to the observed frequency? What do you think? So first of all, if this observer is also stationary, let's say, assuming if this guy doesn't have any velocity, so let's call this v equal to 0 meter per second. All right. So the wavefront, let's say I am the observer. So the wavefront that hit my ears is going to come in the normal rhythm. It's just like bam, bam, bam. So that's a regular frequency that is generated by the source. So let me name that frequency to be F sub S. So that is the source frequency. You guys with me? All right. So the wavefront from the source will just crash my ears like bam, bam. Let's say one round per second or whatever. So every second there'll be wavefront hitting my ear. Bam, 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 bam. So in that case, my observed frequency will be exactly the same as the source frequency. Why not? All right.
Okay.
So it's no big deal. Now, think about it. If I am traveling toward the source, now the scenario will change because I'm moving against the wave. So the number of hits that I'm going to get per second is going to get higher. With me, guys? Yeah, perfect. So that's it. That's the whole idea. So if I'm traveling toward the source, my observed frequency will be higher. I put like an arrow up there relative to the frequency that's generated by the source. On the other hand, if you want to go backward though, so if your velocity going in the opposite direction, so you're running away from the wave. So before the next wave can catch you, it takes more space, more distance. So in that case, the things will be opposite. The observed frequency will be lower than the source frequency. Cool. Is that all right?
Okay.
That's simple. Now, if you get this one, then, so let's agree on the notation that we're going to use. All right. So first of all, we already introduced this subscript S that is for the source. All right. So if I have the source frequency, I'm going to put F sub S. And we use the O for the observer. So if I want to talk about the speed or the velocity of the observer, I put the subscript O into it. So that is my speed of the observer. And of course, you have two directions that you can set it up. So it's either go toward the source or running away from the source. All right. But I mean, we can use interchangeably between speed or velocity, even though we don't do three-dimensional stuff. So that's what it is. And the observed frequency that the observer will hear is going to be F sub O. Okay, makes sense? So far, so good? All right, notation is fine. And then what we're going to have a chance to do is, what if we add the speed of the source? So that means the source could be running as well. So let me put V sub S, and that is the speed of the source. Cool? All right, almost done. But then think about it. Whatever things that you are trying to do, you are trying to generate a sound. It's just sound waves. So the sound itself has to travel. We learned it from the 2 lectures in the past. So the wave itself, the sound, has its velocity. Whoa. Okay.
Okay.
So what we are looking at right now, you have 3 speeds that we are talking about. The observer speed, the source speed, and the wave's speed. With me? Okay, so don't get confused because there are 3 things that is moving right now. Okay, so all right, there's a question comes in. All right, and that I will answer that question, right? What happened with the source traveling? So what you have over here is, if you know the speed of the sound, and if you know the whole set of this one, for example, you might know the frequency of the sound generated, that's from the source, then you should be able to calculate the lambda, the wavelength of the sound as well. All right, if you want to. So that is an easy one. So let me put like a block over here. You can calculate it. Okay, so that is the whole business that we are trying to do right here. So this is the speed of sound. So we left the no subscript velocity for the speed of sound. Sounds good? So in conclusion, we're going to have speed of sound, observer speed, and the source speed. There are 3 speeds right now. Okay.
Okay.
It looks complicated at first, but it's not that bad. All right, so here we go. Everyone staring at this slide, and how do you feel? What do you think? It's like, I don't know, some of you just don't like this. It's like, Ajahn, again, you said that we're not going to do a lot of like derivation or proof or anything. All right. And once you staring at this for 10 seconds, 20 seconds, yeah, you can move on to the next. Then blah blah blah. I mean, I can go through all this stuff if you like. However, it's all algebra. It's not that bad. But some of you just hate doing this because, man, at the end you just want to know how to apply this thing. So let's take a look at this. Okay, let's discuss the case that we already sort of completed. That's got you guys got that one. So if the observer moving toward the source, the observed frequency will be higher. Let me put a note over here. And if the observer moving away, the observed frequency will be lower. Everyone agree with this? This one's good. All right. Now, instead of showing the derivation or trying to prove this to you, I want you guys to take a look at the final results and try to understand this. Here, at the end, this is what you get. The observed frequency is some multiples of source frequency. That's good. So you have some factor in the front. And look at the factor. Isn't that cool? So the V itself is just the speed of sound. That's the sound. This is observer. And then as you can see, in the case of running toward the observer, this bracket over here has a value larger than 1. And that's make perfect sense because you guys know that when the observer moving toward the source, the frequency will be higher. So the factor in the front will be larger than 1. Cool?
Okay.
Now move on to the next. If you compare this one to the bottom expression, what do you see? The observed frequency, the bottom one is the case that the observer running away from the source. The form look exactly the same. It must be some multiple of the source frequency. However, look at the numbers right here. See that? You have the negative sign in it. So in this case, what you are getting for this brackets over here is going to have a value less than 1. You guys with me? Okay.
Okay.
And that means that make perfect sense because we know in that case, the frequency should be lower than the source. Keep this in mind. All right. Just park it here. Let's move on to the next half of the whole analysis. Even though I'm not trying to derive it again, but this will answer your question about what happens if the source is traveling. So just make a simple case first. Let's say now I keep the observer to be fixed. So it means there's no speed for the observer. So visible is 0, just for simplicity for now. The case stays the same in the case that now, if the source moving toward the observer, what do you think it will happen? You can see right away that because the traveling direction of the source is toward the observer, the wave front will get squeezed in. Does that make sense to you? Because the new wave that gets generated is get generated closer to the wave that is generated before. So that's why if you look at this portion of the wave, which means to the front of the source, this area over here, you will see that the wave front gets squeezed in due to the movement of the source itself. Make sense to you guys? And of course, if you want to contrast this right away about John, what happened toward the back? Of course, you can see from this toward the back, the spacing between the wave fronts will get extended. It's going to get more spacing. All right. So now you have your choice to stay in the front or you stay in the back. In this particular figure over here, when the observer is in the front, what do you think it will happen to the frequency observed? Of course, the frequency observed by the observer will be higher. Why? Because your wave fronts get squeezed in. So it means the number of hits that it gets to observer's ear is going to get higher than usual in relative to when the source is not moving. Okay?
Okay.
Got that one? And if you are toward the back side of the source, now the spacing gets stretched out. So the number of hits that you're going to get to listen to is going to get separated. So it's going to get number of hits getting smaller. So the pitch that you're going to hear is going to be lower tone. in this case, the frequency observed will be lower. In conclusion, that's it. If the source moving toward the observer, you're going to observe higher frequency. If the source running away from the observer, you're going to observe the lower frequency. Now, look at the expression that you get. I'm trying to do the same comparison here. Look at this. The observed frequency is going to be some multiple of the source frequency. But for this particular case, the source moving toward the observer, look at the ratio, guys. See that? It has a negative sign in the bottom, in the denominator. So what this is, it's telling you that in this case, this factor right here is going to be larger than 1. Got that one?
Okay.
Okay, because you have a negative sign in the bottom, so the ratio is going to be greater than 1. And now you can guess what should happen in the case of the source running away. But no problem. In that case, the observed frequency, right, will be some multiple of the source frequency. But when you look at the ratio, that factor over here, in this case, is going to be less than 1. Oh, did I say less than 1? Yeah. All right. Less than 1. And that makes perfect sense. Check. Done. Cool. I don't know what's cool, what's not cool, but that's the easiest way that I can give you an idea of how to deal with this if both of them are moving. All right. Both of them can be moving in whatever direction that they want. So that's the only thing that I want to give you. That's it, guys. This is it. Oh, no need that one. Look at this one. How do you feel? What kind of question is this? How do you feel? How do you feel? I feel sleepy or whatever. Oh, I have my own coffee right here. I can get 1/0. I think you think too much. All right. So the expression that I'm trying to present to you right here is you're trying to calculate the observed frequency that's on the left. Okay. Now, whatever you get, you're going to get some factor in front of the source frequency. So whatever the value that comes in the brackets over here is going to modify the source frequency. And you already have seen all the cases. It could be higher, it could be lower, depends on the movements of the source and the observer. So if I want to combine them, so both could be moving, here we go. All I need to do is just take whatever that we got over here, along with whatever we got over there, and we do combination of those. So it means we can do the analysis one more time if you want to. But at the end, this is what you get. On the top portion over here, that's related to the observer, just like what we did in the first 2 cases. And in the bottom over here, that's related to the movement of the source. That's the later 2 cases. And that's it. This is the only expression that you need for Doppler effect calculation. All right, just to make things even more explicit, what I'm going to do is I'm going to show you how many cases that we can do. All right, so let me add a page over here, and I'm going to give you the whole grand conclusion, guys. Seriously. And for this, you can pretty much solve, we call it like a Doppler effect in the one-dimensional problems, pretty much all of them, let's say all of them. Okay, here we go. So in conclusion, this is, think of it like a summary, all right? But this is all you can think of it like an application. So you have an observer right here on this side, could be traveling, that's observer. And then you have, here we go. Oh, let me put the source on the left, just so it's coincide with most of the figure that we already had. So this is the source. This is observer. Okay, sounds good. All right. So what we can happen, what could happen is if the source traveling in one direction and then observer going opposite, so it's mean going against each other. Okay, what will happen to the observed frequency? So what I'm writing like this here, this is what I'm doing. I'm going to write it like this. F observer, that observed frequency is going to be some numbers multiplying the source frequency. And this ratio right here depends on the speed of sound. Can you see this from this formula? You always have this. And is going to depend on the observer speed on top and the source in the bottom. That's the form of it. That's all we had from those 4 cases that we considered. Now depends on what are going to be the sign that you're going to put in. Now, when you look at the observer, this is what I'm going to show you. I don't know if this works for you, but if it works, then you can take it. Observer moving toward the source, what happens? You said the source, the observer will hear the higher pitch. Whereas the higher pitch means you have an opposite effect to the final observed frequency. So in that case, I'm going to put positive sign in it. You guys with me? So the numerator is supposed to have a bigger value because you're supposed to enhance the observed frequency. Now turn our attention to the source. The source going toward the observer, what should be the effect? The effect should be higher frequency as well, right? Because the source going toward the observer, you should hear the higher frequency. To make things higher, that means the number is supposed to get bigger, but because the source speed is down here, to make this ratio even bigger, you pick a negative sign there. And that is done.
Okay.
Try again, right? If you start off like, okay, a little bit. Another case that's possible is the source running one direction and then observer running away. So they're both running in the same direction. So the observed frequency in this case is going to look like this. See, this is what I'm going to do with like a million times today. See, this is the form of it. It's going to be something like this. And then now look at the numerator. Is the observer side, observer running away from the source. The effect supposed to be the lower frequency. Lower mean smaller number. Now look at the source going toward the observer. You don't have to care if the observer running away or towards. I don't care now. I only care about the direction of the source. The source is trying to catch up, or it's the source trying to overrun or whatever. I don't care. But the source is running toward the observer. So the effect is going to be higher frequency, right? To get the higher frequency, it means you have the smaller denominator. So you put a negative sign there. And that's it. Done.
Okay.
Got that one? Try again. You start to get the feeling what is going on. If the source running in one side and the observer now running in the same direction instead. Okay. So in this case, what will happen? So once again, it's going to look like this all the time. Yeah. It's kind of like start to get tired of this. And then now look at the observer side. Observer is running toward the source. The frequency is supposed to be higher. Pick the positive sign in the front in the numerator. And then the source running away from the observer, the final effect supposed to be lower the frequency observed. So you put plus on here because you want you want a smaller number at the end. All right. And then I think you can guess what should happen now in the last case. What if they are moving apart? The observed frequency will be something of the source frequency. The numerator depends on the observer speed. The bottom is the source speed. And now you can guess. Okay, once again, start with the observer. Observer running away, the effect is lower in frequency. Lower means smaller number in the numerator. The source running away from the observer is lower the frequency. To get something lower in frequency, you want the bigger number in the denominator. And that's it. Done. Wow. All right. It's too much. I think it's too much already. Okay, guys. And that's conclude 4 cases. What else can you have? You can have only 4 cases here because you are moving in one direction. It's a linear line. So these are all combinations possible. Okay. Can you explain the second equation? Okay, sure. The green one, okay, the second one, now the observer running in one side, the source running in the same direction, okay? But in this case, the source is toward the observer. Okay, so what you have over here, I can rerun this one. So what I'm doing is I'm just gonna have to pick the correct signs. Okay, start from the observer, observer running away from the source. Okay, observer running away. So the effect of the observed frequency should be lower. Okay, lower means you want a lower number in the top, in the numerator. Yeah, smaller number, smaller the observed frequency. But now look at the source running toward the observer. The effect of the source running toward the observer is to increase the observed frequency. Yes. However, because everything about the source is in the denominator, to make the final results have a larger value, you need a smaller denominator. So you pick the negative sign in the bottom. Does that make sense? So I try to sort of like boil everything down into just picking the signs in the Doppler calculation right here. Okay, I hope this is good. I don't know, it's kind of like sort of get it. All right, don't worry. If you sort of like, okay, it's like 50-50, kind of see an idea what is going on, of course, let's attack some problems, shall we? All right, and then you'll see exactly what is supposed to be done using these expressions over here. All right, guys, take a look at this. So you have a train that is moving parallel to a highway with a constant speed of 20 meters per second. Now you have a car that is traveling in the same direction as the train with another speed. The car horn sounds at a frequency given 510 hertz, and the train whistle sounds at another frequency 320. See, information is just floating around, but that's not too bad. What I can do right now is just drawing some figure over here. So assuming that there's like a train running, okay, the train is supposed to be like that. Okay, I don't think there is something coming up anymore, but that's like an old style, you know, like a old style heat engine. All right, you burn some coal and other stuff to run the train. Okay, here we go. So what we have over here is the train that is traveling at the speed of 20 meters per second. Okay, so let me call this speed of train right now, V sub train. Now there is a car, but now let's look at the part A. When the car is behind the train, what frequency does the occupants of the car observe for the train whistle? So it happens that there is a car running 40 meters per second. Let me call this V sub car. There you go. But it's still behind. All right. And then the train whistle the sound frequency beep, 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 of 320 hertz. That's the sound from the train. The car itself horn sounds at 510 hertz. Okay. Now, first question, how can you calculate the observed frequency by the car passenger? F sub O equal to something F sub S. With me? And you can even set up the infrastructure of the whole thing. There you go. But now you have to know which is which. Which one is going to be your observer? Which one is going to be your source? For this particular case, the observer is going to be the one that's sitting in the car. So that means the V observer over here is going to be V sub car. You guys with me? And the source coming from where? Coming from the train. So that means the speed of the source that is going to be the speed of the train. Cool. All right. So I can sort of like mark this to be like here. This is the observer O, and this is the source S right there. All right. Now we can start doing it right now. The source is running away, the observer running toward the source. Let's attack the numerator first. The observer running toward the source, what happens? So you're supposed to get higher frequency, yeah? Yeah. With me? Now, what about the source? The source, the train, running away. The effect supposed to be lower in frequency. Okay, lower in frequency. But to make things lower, for the denominator, you need a positive sign there. Cool? It's kind of quiet. Yeah, okay. Yes, I hope. All right. So if this works, then the rest that need to be done is just plug in the number. So let's try plugging it in because we want to make sure that things is correctly put in. So the speed of sound, usually it will be given. Maybe like 340, 345. So this is like something that's given to you, even though it's not written here, but most of the question or the problems will have some note saying that, hey, the speed of the sound is equal to what? So I can use like 345. That's kind of nice number here. Okay. And then you plus the speed of the car. In this case, is 40 divided by 345, speed of the sound, plus the speed of the train is 20. And now, what about the source frequency? The source is the train at this point. So it's going to be 320 hertz. And that's it. These numbers will give you the observed frequency by the passenger in the car. Cool. And one thing that's my sort of like emphasis on this one, can you see the final ratio over here? It's larger than 1 because it's plus 40 on top, plus only 20 in the bottom. So actually the final observed frequency will be higher. And that makes sense because the car is actually catching up with the train. Can you see that? The car is actually moving faster than the train. So actually it's approaching the train.
Okay.
All right. So in the like sort of like an effective movement relative to each other, the cars is actually approaching the train. So that's why the net observed frequency should be higher. Okay, got that one?
Okay.
Where did you get, okay, 345 is given. 345 is usually given. So maybe like take V to be 345. That's sort of like given meter per second. There you go. Okay, sounds good. Okay, try again for part B, shall we? So that's part A. Okay. Okay, everyone try part B and see how it goes. Try part B, guys. That's going to be good. There you go. Now, for the part B, you have to make sure that you get this whole thing right. Part B, the car is already in the front. Woohoo! Right there. It's already overtake that train already. So it's still the same speed though. 40 meters per second. Everything is fine, but now it's in the front. It's still honking the same horn. There you go. Now, set up the observed frequency for part B. Okay, be careful here. So what we want is, once again, the formula looks exactly the same. I just laid out the infrastructure again. There you go. But then, because this one, what they want is the observed frequency by the passenger on the train. So that means for part B, observer now turns to be here. So let me put prime in it so it's separate between the part A and part B. So the observer for the second part is now the train. And the source, let me put prime in here. That is the passenger in the car. Cool. So just to make it clear, let me put prime in all of these so it won't get confused with the first part in the part A. All right, so you make sure that you put the correct value into this. And just to be clear, now the observer for this particular case is now train. And the observer for this particular case is now car. So the speed of the observer will be the speed of the train. The speed of the car will be the speed of the source will be the speed of the car. Okay, now pick the sign, guys. Oh, does somebody submit the answer? All right, well, we'll check. All right, look at the observer first, the train. Now the train running toward the source. Okay, the train now is an observer. The train running toward the source, the effects should be higher in frequency. So I'm going to pick positive sign here in the front. Higher frequency. Now look at the car passenger is now the source. The source running away from the observer. The final effect should be lower in frequency. But because everything is in the denominator, to get things lower, you need a bigger number down here. Bam. Got that one?
Okay.
Cool. So actually, they are pretty much the same. Part A and part B are exactly the same scenario. Okay, because it's the case of this one right here. The blue one is the blue case. The source running in one direction and the observer is catching up, or it doesn't have to be catching up. It's just like going in the same direction. And in this case, it's the same thing, except that the value that you're supposed to plug in is going to be different from part A, because it's going to be 345 plus now it's going to be the speed of the train, so it's 20 in the top, and 345 plus 40 in the bottom. And the source frequency now is going to be the horn sound from the car. Right? You make sure that you get these numbers right. But once you get it, it's done. Okay?
Okay.
And once again, you can observe the value that you're getting over here. See this? The ratio that you have is now less than 1. Less than 1. So what does it mean? It means that the passenger on the train will observe the horn sound to be lower in frequency. And that makes perfect sense, because look at this scenario over here. The cars travel faster than the train. So from the perspective of the passenger on the train, they will see that the car is actually going away. It's running away from it. Yeah. So things running away will generate a lower pitch. Okay, perfect. So that's it. So this ratio should give you less than 1 value. So you should hear the horn sound of the car has a lower tone. I mean, not tone, lower pitch right there. Cool.
Okay.
All right. So as you can see now, the application of the Doppler effect is not bad anymore. Okay. Want to try again? One more time? Yes, maybe. Oh, somehow participants is lower in number. Or maybe it's already 12. That's just my bad. I thought I saw like 14 before. It's like people start to leave now. It's like getting worse and worse. All right, guys. This is going to be the final showdown on this one. It's like, this is a huge, well, I wouldn't say huge, but a huge in the sense that usually I put this in the final, not the final, in the exam. So the exam question will not be harder than this example. All right. So the first example just showcased how to apply the Doppler effects formulas or expressions, and how to correctly put in the values, how to set things up correctly, which side is observer, which side is source, and make sure you get the directions and signs correctly assigned. Here, one more time, but this is the coolest questions that we are going to meet in the Doppler effects. All right, you want to try that one? So we're going to spend this one, spend time solving this one, and then we'll take a break after this. Sounds like a good plan. All right.
Okay.
You want to give it a shot first, guys? At least may try for a couple minutes, set things up. At least read this whole thing first, and then whatever comes into your mind, that will be what supposed to be done later, all right, in terms of the actual calculation. Okay, a bat, which is, all right, we guys know it cannot see things. It used like a ultrasonic waves, supersonic stuff, all right, and just try to, well, it's not listening, but it tries to sense the echo, the leaflets from those wave that it's sort of sending out. So a bat moving at 5 meters per second. So there is a, let me call V bat at this point, is chasing a flying insect. So there is an insect, something here, and it's chasing. So we assume that, well, assuming that the insect's supposed to travel somehow with the insect. Let me put I here because we haven't had any subscript I, so that should be good. And that is some unknown meter per second. Let me put X in there. Now, if the bat emits 40 kilohertz chirp, so it means there's some super high pitch, super ultrasonic sound that coming out from the bat, that is 40 kilohertz, and receives back an echo. Whoa, 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 this is good. So somehow the bat received back the echo from the insect to be 40.4 kilohertz. Now, the question asking you to figure out the speed of the insect. And even though it's chasing, in reality, you don't really know exactly which direction the insect is moving. So that's why the problem asks you, is the insect traveling toward or away from the bats? Wow. You want to give it a shot? Okay, so this is kind of like, is a very good examples that showcase the application. So let me take this time to talk about the application right away. So at the same time, you're probably like processing this whole thing in your head too. Or maybe not. All right. So what you have over here is you're sending out some frequency, you receive back the echo, but the echo has some signature on it. In this case, is higher frequency. And if we can solve this problem, that means it's going to be exactly the same scenario that you see like a policeman or whoever sending out a signal, and there is like a car traveling, and then this device try to catch up what is reflected from the car, and this is the thing of it, like a speed checker or speed measurement. So you try to measure the speed of the traveling car. I mean, you saw policemen use whatever, the gun or whatever, shooting at the car, or there's like a camera sort of like looking at the car that's moving, and then you can check the speed right away on the highway and other stuff. That is the same Doppler effects. With me, guys? That's the idea. All right. Or, for example, if you have a blood in your body and your blood cells moving, I mean, your blood is traveling with some speed. So what you can do is you have a device that's sending the signal, and by reflecting that signal back from the moving of the blood, you can check the speed of the blood flow. And that's how you can measure your blood flow in your body, by using the Doppler techniques as well. Isn't that cool? Or on the other hand, if something is moving in outer space, oh, you can think it's outer space. There's like a big star, smaller star, whatever. All right. But this one, okay, it might not be like a speed measurement per se, but what you can think of it is like, if this thing moving, the frequency that you receive changing from it's supposed to be when it's stationary. And that's how you have a signature showing that something is moving. All right. So see that the Doppler effect is a very, very good indicator of something that is traveling, and it's changing the frequency that it turns out coming out of it, or coming out from that thing that is traveling. So this is a very good tool that allow you to determine the speed of something by you don't have any contact. So it's like a non-contact technique to measure the speed. So Yeah, you always get the speeding tickets. Probably that's you have to pretty much blame the Doppler effect right here.
Okay.
All right, guys, come back to our problems over here. How can you measure the speed of the insect without touching it? At this point, you send out the waves and receive the echo. The change of the echo frequency allow you to determine the speed of the insect. Perfect. This is the application that I need. Okay. So the way to do this, things that I said is not going to be more complicated than this, is because this is two Doppler effects calculation in one. Whoa. Wow. What I'm saying over here is this. You have the two directions of the wave. One is going away and one is coming towards the source. So let me have this one, put it in two halves. The upper half, the bat is an observer and it sends out the wave toward the insect. So the insect is, sorry. Opposite. Come again. On the way toward the insect, the bat sending out the signal. So the bat is now the source and the insect is the observer. Cool. That's the first half of this whole process right here. But once it's done, whatever the insect hear, even though it doesn't have to hear it, but at least whatever the wave hits the insect, it will get reflected back right away. So on the way back, the insect will behave like a source now. But let me put prime in it just like before so you distinguish between these two halves and send back the echo toward the bat. So the bat now turn into the observer in the second half of the calculations. You guys with me? But the good thing about this one is whatever the observed frequency that the insect receive in the first half of the calculation, that will turn into the source frequency in the second half automatically. So you get the point of what we are trying to do now. So you split this into two sections. The first is the one that the bats emit the sound toward the insect. So first half is just the calculation of what is the frequency that the insects receive. Let's do that, shall we? All right. So in the first half, the observed frequency. Oh, what happened? Okay. First half, observed frequency. Let me put the infrastructure right here. There. Okay. And just put a quick note in here that the observer speed is going to be insects. The source speed is going to be the bats. Yes. Cool. Now, pick the sign for me, guys, for the first half. So you can see that the source moving in this direction. And because we don't know exactly what is going on, so that's why I put the arrow sign for the insect to be on the right as well with some X meter per second. So let's take the right direction to be the direction of the insect. So if this is a setup, what should be the sign that we pick, guys? No, don't need that one. Okay, so the source running toward, let's start with observer, right? The observer running away from the source. The effect should be lower in frequency. Lower in frequency means smaller number. You put negative sign there. Okay, now turn our attention to the source. The source running toward the observer. The effects should be higher in frequency. To get things higher in frequency, you need smaller number in the denominator. So you put a negative there. Cool?
Okay.
Got that one. All right. Now plug in the number for now. So it's going to be equal to the speed of sound. Now it's given to be 340. So that's why it's 340 minus. I want to put the numbers in at this step because I just want to double check that everyone can see which number is supposed to go where. So minus the speed of the insect. This is X. Over the bottom, 340 minus the speed of sound. The speed of the source is 5. Okay. And the frequency of the source right now is 40 kilohertz. It's up here, right there. That is the first half of the calculation. Okay, cool. Next, let's look at the bottom half. Look at the blue, All right, for the blue, I set up the infrastructure again, but let me put prime into this. So distinguish the two halves, source prime, V, VO prime, V, and S prime. Okay, so now in the second half, the observer back to the bats. So here it's going to be V bats. And the source is going to be the speed of the insect. So it's going to be insects, V sub I, down there. Now, picking the sign, guys. So look at the blue. The observer, which is the bat, running toward the insect, the source. The effect's supposed to be higher in frequency. And because you want a bigger number, you add positive sign there. Okay, let me put the blue color there. Okay. What about the source? The source is an insect. Insect is running away from the observer. The effect should be lower in frequency. Lower in frequency means you need a bigger number in the denominator. There you go. Almost done. All right, let me write down the number. 340 plus the speed of the bat is 5. Down here, 340. The speed of the insect, X, and Fs prime. But we have already agreed that the frequency that we're going to use for the source in the second half comes from the observed frequency from the first half of the calculation. So that means what I'm going to do is I'm just going to grab this F sub O from the first half of the calculation and use it here. That's what we agree on to do. There you go. Ooh, right there. No, that's dirty. Okay. All right, cool. So what I'm going to do is just take the whole thing in. Go ahead. 340 plus 5 over 340 plus X. Now I'm take the whole expression and put it there. All right.
Okay.
Plus, I know this final observed frequency is what? 40.4. So actually this number is supposed to be equal to 40.4 on the left side. Can you see this? The last line of this expression over here has only one unknown, which is the one that we want to calculate, is the X right there. And that's it. From here, you can solve for X. X equal to some number, and you are done.
Okay.
All right. Now, the good thing about this equation, just like what we always did in the past, in the thermodynamics, all the stuff, the sign will be automatic. As you saw from here, you don't have to worry about which one moving faster, which one moving slower. I don't care. The mathematics will take care of the final results. You only care about the direction, right? Over here, same thing. If the X that you solve from this equation give you positive number, that means your assumption that the speed of the insect, the speed of the insect that is traveling to the right direction, this is already correct because you get a positive number at the end. But I mean, don't be afraid if your final solution, I mean, the numbers that you got is a negative number. That means your final direction is going to go opposite. So it means the insect is traveling toward the bat. Got that one? So it's kind of cool.
Okay.
Right? So the mathematics will take care of everything. So your job is just solving it.
Okay.
All right, guys. So I think this is a good point to break, and then that's close the topic of the Doppler effects. All right. And I hope you see some good applications of this. Oh, somebody got the numbers. Thank you very much. I think I trust you. It's 3.3. So it's positive then. Cool. So it's the 3 0.3. I expect that it's meter per second, right? Not millisecond there, right? Thank you very much. All right. The rest of you guys can double check your friends' work as well if you want to. All right. So, and let's take a break right here, guys. So what we are going to do next is another property of waves that is, I would say, is very important and is kind of like it's set up the whole business that most of us will be doing in the future. Actually, we have been using this for pretty much everything. It's about the superposition of waves. Okay. So now the question comes into the point where what happens if you don't more if you have more than one waves. Okay. So in general, what you can do is you need to know how to manipulate waves now, because you can have multiple waves meeting at a point, and then you want to know, hey, what is going to be the final outcome of those combinations? Yeah, it's a simple question of that. And yeah, okay, that's good. There's some suggestion there. You're right. So the thing is, what we are trying to get to is we try to get to the algebra of the waves. It's an algebra. So the thing is, it turns out we have a very simple principle that the waves seem to follow. Well, I would say most of the time, not all the time, but most of the time. And that principle has a name, is superposition principle. And the good thing about this superposition is very easy. It's linear, guys. We love linearity. When everything is linear, 1 plus 1 is equal to 2. So look at a simple description of this one. If you have two waves and it's waves on a string, so you have one on the left, one on the right. Now you have two waves on string, and then they meet in the middle. What happened in the middle when they're trying to pass each other? You just add them up and you are done.
Okay.
That's it, guys. That's what we have today. The rest, oh, no, just kidding. All right. So what we have right here is now is a simple additions. That's why the algebra is easy. Second thing, look at this one. Waves never stop. All right. You cannot do anything with it already. Once you disturb it, the disturbance get propagated and that's it. It's gone. Just boom. All right. So once they meet, they're just going to meet like temporarily. And then once they meet, they're just passing each other by and that's it. It's done. So that's why at the end, everything just go business as usual. The waves just keep traveling. All right. But at the meeting point, the mathematics is simple. Summation, linear summation. So when you say linear summation, so Ajahn, it's possible to have some cancellation then. Well, yeah, of course. So look at the second case. If you have the second wave from the right, turns out to have the opposite displacement. No big deal. You still sum them up. No change. But it's just the displacement is in the negative direction. So at the end, you get some cancellation effects. So the case that you can have like a constructive additions or destructive additions then lead you to another property of waves. We name this interference. So wave can interfere with each other pretty much. So you can have an interference of wave. And to take into account these interference effects, you base everything on just a simple principle, superposition of waves. Okay, so I hope you see the relationship between these terminologies over here. All right. So there's a question comes in, don't the waves lose some energy when they interfere? Okay, so we assume that if it's in the ideal case, no, it won't lose any energy. It's just passing each other by. That's all. And the medium at that point take into account the overall effect of the disturbance, and then the medium itself can decide how much they would like to move on and on. Okay, sounds good. So the energy, it depends on the property of the waves itself. If the propagation of that wave is like it's like a perfect wave, there's no losing an energy of that wave, the interference will not lose any energy as well. Okay, all right. So here we're gonna call the first part of this one when the end effect give you a higher result or a higher displacement of the medium to be a constructive interference. And on the other hand, if the results after the additions give you a lower displacement of the medium movement, that is going to be a destructive interference. Okay, sounds good? All right, but we're not going to keep doing all cases like, okay, that's some weird shape. We're not going to go crazy, calculate waves that has a shape that looks so odd and everything. So we're just going to look at our beloved sinusoidal waves. Why not? Yeah, right? Because we have learned so much about this and we know the characteristic of waves very clearly by reading out what is going on from the shape of the equation or the shape of the sinusoidal expression itself. Let's take a look at the first one, guys. Quick review. Remember this? Yes, amplitude A, wave number K, angular frequency omega, and just a quick reminder, this one is 2 pi over lambda. So from the K, you get to the wavelength of the wave. The omega is 2 pi f or 2 pi over period. So knowing the omega, you know the frequency of the wave, you know the period of the wave. Once you know the K, once you know the omega, you know the velocity of the wave to be f lambda. All right. And just to be sort of like, more fluid and very sort of like quick in calculation, if you want to, I can multiply 2 pi on the top and the bottom if I want to. And you can see that the 2 pi f is just omega and 2 pi over lambda, that is just K. So actually I can say this omega over K as well if you want. Cool. All right. So that's what you can do is, well, now you know how to read the wave. And the negative sign in the middle is telling you that the wave is traveling in the positive X direction. Done. Now look at the second wave, guys. Oh, Adan, that's not bad in comparison to the first one. It's just the same thing. Amplitude, same amplitude. K, same K. Omega, same omega. The only thing that is different is now you have this extra phase difference, which is fine. We already learned this one. That is just the original wave, but you slide it. You sort of move things around a little bit, right? And phi just give you an idea how far you want to move. One reference that is easy for you to do is if the phi is exactly 2 pi. Love it. If this is exactly 2 pi, you get exact same shape of the wave back because you completely slide it, complete one full cycle. Okay, sounds good?
Okay.
All right, so now what happened if you have these two waves and then you try to combine them all? Well, no big deal. All you need to do is just sum them up. That's how easy it is. I am serious, guys.
Okay.
It's simple like that. But the only thing is we want just to make things look a little bit nice and, neat and all. So I would like to recall one identity that I don't know if you still remember this or not, but I have a reference right here. When you have two psi functions adding to each other, you can turn it into a product to be the two numbers in the front, sine and cosine. It's the sine of the average of the two and the cosine of the difference over two. I don't know if you sort of like vaguely remember this or have seen this roughly. All right. But back in the day of trigonometry in mathematics, you probably like psi A บวก psi B เท่ากับ2 psi A cos B อะไรสักอย่าง something like that. Yeah. All right. So there is some sort of like formula that you might have to sort of memorize in your head. All right. But we don't need memorization now at this point. So I can turn that summation into a product. So let's do that. So I have two. A is just common factor. I pull it out. Okay. And then attack the difference first. The cosine of the difference. So the difference will cancel the kx omega t, kx minus omega t out. You only left with the phi over 2 in the cosine factor here. And then for the sine, you just add them divided by 2. So you have 2 of that kx minus omega t, and you sum and then you divide it by 2, you get back the original. So it's kx minus omega t. And then you just have extra phi over 2 in the back. All right, very good. When I say very good, What do you see here, guys? Can you tell me what are you seeing? You have to say about Ajahn, it's still sinusoidal wave. Cool?
Okay.
If you can tell me that, then that is very good because why? K, omega, direction. Translation sliding a little bit, that's okay. But it is still sinusoidal wave. I see an equation. Okay. So the only thing that is different now is the factor in the front. Oh, too much. Sorry. The factor in the front. It just look complicated, but nothing more than I will call it this another amplitude. Why not, guy? This is amplitude. But it's just the new amplitude, right? And you can calculate the new amplitude by substituting whatever the things in here. Yeah, 2a cosine phi over 2. If you can get these numbers out, that is your amplitude of the resultant waves. That is done. Okay.
Okay.
But the good thing that sort of like hidden in here is the cool thing about this phi over 2. Do you notice something here? Let's make it so nice. The phi over 2 here is under cosine. And you guys sort of remember this. Cosine 0 is 1. Cosine pi over 2 is 0, which is 90 degrees. Okay, and then you can keep going. Cosine pi is minus 1. Cosine 3 pi over 2, that is just 0 again. And once you complete one complete round, cosine 2 pi is back to 1 again. Okay, but what we are really interested in is just the extreme cases here, 1 and 0. Negative 1 is the same thing as 1 because eventually it's going to go back and forth between 1 and minus 1. So you see that if phi is 0 originally, what does it mean if you pick phi to be 0? That is your first case right here, guys. See that? When you pick phi to be 0, that means two waves are exactly the same wave. So you have two waves riding on each other. It's sort of like overlay on top of each other. So that's why the first figure on the top right here, you only see the blue because actually there are two waves on top of each other. And the red curve is just the sum of the two. But because these two waves look identical, that's why you double the amplitude. So if you try to substitute phi equal to 0 in here, you can see that the amplitude here, the 2a cosine phi over 2 is just 2a because cosine 0 is 1. With me? So that's why you say the amplitude of this one is a. The resultant amplitude is 2a. You double that. The height is double. Yeah, there you go. That's a. That is 2a. See? And that you have a constructive interference. Plus, because this is so perfect in combination between these two waves, they are oscillating in rhythm, in sync. In physics, we name it in phase. Whoa. All right. So it's in sync, it's in phase, it's, I don't know, together. So it's, don't forget, wave never stop. So that means this thing has to travel. But then the idea is it's travel at exactly the same. So if you think in terms of oscillation, so these two waves copy each other. So everything is just on top of each other. So this is an in phase. Okay. Now you can look at the other extreme. If I want to make this amplitude, the new amplitude, to be 0. So what can you do? But then 2a cosine phi over 2 will go to 0 if pi is equal to, I'm sorry, if phi, that extra factor, if phi is equal to pi, 180 degrees. So when the phi is equal to pi, you get the cosine phi over 2 to be 2a cosine pi over 2, and that is 0. Now look at the second figure. That's what it is. You have the blue and now the green showing up. That is another wave. The green and the blue combine and is destructively combined. The final result is 0. 0 wave as a resultant wave. And this, we call it an out of phase. So when they say out of phase means the two waves will oscillate in opposite direction at all time. When one reaches the peak, the other one will reach the peak in the opposite direction. Okay, with me? And then it just go up and down. So it's out of phase, perfectly out of phase. Okay, so that's why the net result is just 0, zip, nothing. All right, so these are the two extremes that representing the full constructive interference and the destructive interference. And if you want to go somewhere in between, you know, like, hey, I want to go, 60 degree, pi over 6, pi over 4, you can just plug in into this expression. And what you get at the end is just going to be the resultant wave that you see intermediate between these two extremes, the red curve right there. Okay. But the amplitude of this one can be determined from that expression right there, 2a cosine phi over 2. And that is the whole concept of superpositions and what you get as an interference at the end. Is that simple enough? I hope it's not too complicated. So keep in mind, all you're doing over here is just adding numbers. Okay, but instead of just a pure number, you get a sinusoidal function to add, but it's still addition. It's a simple algebraic addition. Okay, all right, so that's good. And I hope you sort of like get the feeling of what is going on about the phase a little bit better, because every time that we discuss something behind this sine and cosine, sine and cosine, sine and cosine, sine and cosine right here, whatever here, or you name it, phase, just phase. So, I mean, if you want to link back to geometry, that is just angle. But for us, because things keep repeat itself, and then you want to pinpoint the position in the angular units and all the stuff, so you want to name it differently. You name it phase. Okay, so phase is equivalent to angular position in circular motion, or in, something that's travel in circle. Same thing. Okay. All right. Any questions so far? Seems easy enough, I hope. Yes. All right. Yeah. All righty. Okay. All right. So what happened in reality though? Well, Ajahn, that's fine. You just gave us like two sinusoidal waves, and then you just sum them up, and you just go crazy a little bit using some identity, and then you just, do this and do that. And then, but in reality, where can you observe this interference? That's the question. Okay. So in reality, you're probably not going to see this because in real life, well, it's hard for you to observe this because you need a sinusoidal wave source. So that means you need the source to be sinusoidal for you to be able to observe this kind of like interference patterns and other stuff. But anyway, what we can mimic, or at least get the idea, is this. And actually we can do experiments, right? If we meet in class, it's not perfect, but I can mimic the idea of what is going on. So think about this. If we need two sources. So that means you must have two sources generating waves, okay? And then let's say you are trying to observe that waves that reaching you from those two sources. But then let's think about it, that the source might come from one distance, the other one come from the other distance. So you don't really know, once those waves reach you, which position of the medium is about to move. It depends on the phase, right? It could be in sync at your position. So if this is the case, what you are hearing is going to be a louder sound. You guys with me? On the other hand, if at your position, the wave that reached you is perfectly out of phase, it's opposite direction. So you're going to hear nothing because it's going to be completely destructive interfere at your position. Or it could be somewhere in between. It might just, just sort of follow each other. So you hear somewhere intermediate between the completely quiet sound or the loudest sound. Okay. So that means what I can try to show you is, well, let's talk about the distance, shall we? Because in reality, wave has to travel some distance before reaching the observer. So let's assume that the first wave takes some path length. Let's call it R1. The second wave travel another path length. Let's call it R2. My question is, how can you determine at your position that the wave is supposed to do this in sync, or supposed to do this out of sync, out of phase, or somewhere in between? How can you determine that? By knowing the distance from the source. Okay, the idea is very simple, guys. Simple enough that I don't know this figure is good or bad. To me, it's it doesn't make a lot of sense if you don't have these experiments in the like physics lab or something, because this setup is weird. It's not normal. It's kind of like experimental setup for you to observe something. So it might be even better representing what we are doing by looking at here, the problem that we're about to do, right? That's the final problem that we're going to try. This, or actually I have a bigger figure over here, this. So it's probably somewhere you're standing, and then you have two speakers that generate the exact same sound. So let's assume it's sinusoidal waves. And then you're standing here, see that? The distance from one source number one is R sub one. The distance to the source number two is R sub two. That is the path length of each one. All right, so you got the scenario, what we are doing. All right, but in reality, the distance that the waves travel doesn't need to be a straight line. So that's why in this figure, the first wave travel down here, that's R1. And then the second wave, right there, that's R2. That's fine. All right, let's say they take some distance. Now it reaches you. You want to determine, are they going to do this in sync? This, I keep using in sync, in phase, in phase, out of phase, or somewhere in between. How can you determine that? The idea is simple, guys. Think about this. Because we know they are traveling at R by a distance of R1 and R2, right? First case, the easiest case. If R1 is equal to R2, what will happen, guys? Of course, Ajahn, it's going to be in phase. Sure, perfect. This is going to be in phase, 100%. Because they will look exactly the same at your position. Okay, now think about this. What if R1 taking longer distance, but the distance that is longer is just perfect one wavelength? Whoa.
Okay.
What will happen, guys? You're not going to know anything. You got it? I mean, wave just like, okay, man, it's just one wave is sliding more by one cycle, but at your position, I'm not going to feel anything.
Okay.
I'm going to see the wave go up and down exactly the same. Got that one? Or, well, Ajahn, the wave from the source number one could be already two wavelengths away relative to the other distance, the other path length. I'm not going to tell, I'm not going to be able to tell anything. It just looked the same to me. You guys with me now? Get the idea? So that means as long as one distance or one path length is different from the other one by the multiple of lambda, perfect. You're going to get a constructive interference all the time. So that's why all we care about is just, all right. I can just take a look at the difference between these two. See the difference. So if you take a difference between the two, R1 minus R2, and then you don't care which one is bigger than which, because I don't care. It could be R1 is bigger than R2 or R2 bigger than R1. I don't care. So that's why I put the absolute sign to it. And just asking for a multiple, an integer multiple of lambda. If this is the case, what you are getting is going to be, yeah, oop, here, a constructive interference, guy.
Okay.
Okay, got that one? All right, so that's not bad. And now I can start thinking in the same sort of like train of thought over here. Let's start from an outer phase. To get a perfect outer phase, what is your condition, guys? I want the wave to go always opposite to each other, always opposite. So that means it's either R1 is going to be half a lambda. I need these two to slide among each other, half a wavelength. If you can get that half a wavelength, then the difference, you know, is half a cycle. When it's half a cycle, things will go in the perfect opposite direction. Got that one? Okay.
Okay.
And then you do the same way of comparison. It could be, I mean, once you get that set up, but Ajahn, I can add extra cycle to it. Nobody will mind. Nothing will change. I can add 2 cycle after that. Nobody will care. Okay. So as long as you have that have the wavelength in it, you are going to stuck with the outer phase condition. So that's why, once again, if I only talk about the difference between R1 and R2, R1 and R2, what I can set up to do is, once again, just similar to that. I only care about the difference between the two, and I don't care which one is bigger than which. All I need is the path difference between two paths is just odd multiple with the half lambda in there. Oh, sorry. It's like, okay, let me write it down like this. It's going to be starting from odd multiple. So it could be 1 lambda over 2. That's the first case. 3 lambda over 2. That's the one that I give extra wavelength to it. 5 lambda over 2. That's the third case. And now you can keep going and going. As long as you have that extra lambda and a half in it, you're going to lock yourself in destructive interference. You guys with me? All right.
Okay.
And that's what I need. I can just represent my 1, 3, 5, 7, 9 using this 2n plus 1. And then you can start from, you know, n equal to 0. Or for some of you, but John, I don't like this. I want 2n minus 1. I don't care. Same thing. As long as you just having the n running from starting point, like if you start from 0, you might want to use 2n plus 1. If you want to start from n equal to 1, you can use 2n minus 1. But the key is 2n plus 1 will represent an odd numbers when you're running the n as an integer. And then you need that extra half in it. And once you have this, you lock yourself in a destructive interference. And that is done.
Okay.
You guys got that one? Okay, so that's what we can do. All we can, I mean, what I'm doing over here is nothing more than just taking a comparison, or you can think of it like it's, well, I don't want to use it like a unit conversion, but that's the idea that you know the path difference. I want to turn that path into the phase. That's what I'm doing. Because I know if the path is no difference at all, the path difference is 0, the delta R is 0. The phase difference is 0 as well. If the path difference is perfectly 1 wavelength, the phase difference is perfectly 2 pi. All right. So if you care about conversion between the distance to the phase, the common factor that you can use is simply just, we know things travel 2 pi every 1 lambda. That's a factor that you can just use to multiply the path difference to turn things into a phase. That's the whole idea about the phase and the path. All right. I mean, for those of you that sort of looking at this for the first time, I think it just, you know, maybe it's just, it looks very fuzzy at this point, but don't worry. Just sort of stick around doing some problems and try to think in terms of, it's like different part of the question or the different part of the expression. If everything is after the sine and cosine, that is the angle, that is the phase. If everything is outside the sine and cosine, that must be the value that gives you the displacements. That will be the distance, and that is about the path. Okay, sounds good? So it depends on which part of the expression you are talking. That's what I'm trying to say. If you are talking about things that is inside this argument over here, that is just a phase. But once you have that phase, after applying the sine or cosine, you're going to get a number out that is going to be in meter, and that is the displacement. So I don't know if I give you a good relationship between these two sides of the same business over here, but all right, it will get better over time if you see examples here and there. Okay, so let's try 2 examples, and then I think that's it for today. Sounds like a good plan. All right, let's try it. I will show you. It's quite easy once you get a hang of it. I mean, sort of like you get a good grab, and then you have a good grip on this one, and then I think you will be fine. All right, 2 traveling sinusoidal waves are described by the wave function below. Assume as I system, and that's good. What is the amplitude of the resultant wave? See, this one, don't think too much. Whenever you have more than one wave, the resultant wave is simply the summation of the two.
Okay.
Okay, simple as that, and that's it. So I just put them down here. 4 pi x minus 12 pi t. That's from the first. And then I just add the second. I don't know why I have to whisper, but that's what it is. It looks cool. All right, right here. There you go. All right. All right, I just turned 0.25 pi into pi over 4. Just make it a little bit easier to write. And that's it. You can use the identity just like we saw before. You can refer back to this. Okay, the sum is just 2 of the product, okay, with the argument manipulated a little bit. So over here, I have 2, common factor 5, and then you have sine of the first bracket plus the sine of the second bracket. All right, let's copy that identity. So I'm going to do cosine first, okay, and it's going to be difference over 2. So I'm just taking the first, subtract out the second, divided by 2. Okay, what I'm getting is going to be pi over 8. You guys with me? Good. And then I have another factor in the sign, and the sign followed by the sum over 2. Okay, the argument added over 2. So I have 2 of this green underlying portion over here, add and divided by 2. So I get the original back. So it's 4 pi x minus 12 pi t. And then I have negative pi over 8 here. So what is the new amplitude, guys? Anything that come in the front of sine and cosine, you name this an amplitude. Let me write it faintly with that highlights there. That's your new amplitude. So part A, your answer will be this box right there. So the amplitude is 10 cosine pi over 8. Done.
Okay.
Okay, see, that's algebraic sum. All right, part B. What, okay, let me call this part A. B, what is the frequency of the resultant wave, guys? Frequency. What is the frequency of the resonant wave? Don't like this, I guess. Yes, very good. You just read it out. Just read it out. Whatever come in the front of T, that is your omega. Yes, and omega has the information of the frequency that you want in it, and that's it. F is 6 hertz. Done. Woo. See, not bad. It's quite good. Stuck with the principle, and everything is fine. All right, pretty nice. Okay, any questions up to this point? Looks good, looks good. Okay, try again. Last one, guys, for the day. I think already learned too much today, guys. Right, two big uh, concepts. All right, but I hope it's simple enough mathematic wise. No calculus, no complicated algebra. It's just additions, pretty much. All right, now you have a pair of speakers placed 3 meters apart. All right, this one is just the interference in terms of the path, and are driven by the same oscillator, so they pretty much emit the same type of sound. A listener is originally at point B. Okay. So it's right located a meter from the center. So it's good. So point O is good. It's right at the midline between two speakers. Now, the listener then walks to point P, which is a particular distance, which is, okay, it's already at 0.35 meter away from O. Before reaching the first minimum, so this is a very crucial information right there, guys. First minimum in sound intensity. What is the frequency of the oscillator? Can you see where this one goes? So first thing first, at point O, this is going to be perfectly in phase. Yeah? Right? It's perfect because you're right in the middle. When you are right in the middle, the good thing about this one is the distance from the source, number one, and the source, number two, are exactly the same. So there's no path difference. So what I can add on top of this one is delta R is 0. So this, I mean, good. They are in phase to me at point O all the time, up and down, up and down. But now I walk away from my original position. All right. And it turns out, of course, once I move away from my original position, it will not perfectly in phase anymore. It will start to, all right, off a little bit. And eventually, once I reach 0.35 meter, it's completely quiet. That's where the first minimum means. Okay, you got the scenario what we are having. All right. At first, you are perfectly in phase, so it's loud sound. And then when you walk away from it, it's getting a little bit quieter, quieter until it's perfectly out of phase. And that will give you completely quiet sound, no sound. So in conclusion, what you have here is when delta R is going to be equal to what, guys? It's the first time that things get out of phase. So the path difference must be exactly half of the wavelength. Okay?
Okay.
Got that one? Yeah? It must be just half of the cycle. Woohoo. All right. So that's all you need. R1 minus R2. But then when you look at this one more time, wait. I know exactly that R2 is bigger than R1. So instead of, you can start from the absolute, but we know it's going to be R2 minus R1 because R2 is bigger than R1. Must be equal to lambda over 2. Can you figure R1 and R2? Of course, you can use Pythagorean theorem. So what you can do over here is if you look at the upper triangle over here, okay, all right, R1 is just square root of 1.15 square plus 8 square. R2, you just look at another triangle over here. Oh, that looks pretty bad. All right, but you see what I'm getting at? Here you go. That's triangle down here. That's R2. So R2 is just square root of 1.85 square plus 8 square. You guys with me? All right. All in all, you know how to figure out the length R1 and R2. All right. So that's no problem. These two are known. So that means from this equation, you allow yourself to calculate the lambda. So the lambda is known. And in general, you're supposed to know the speed of sound in the air. You can use 345, 340. Usually, to make things perfect in the exam question, I will put like a parenthesis, say, take the speed of sound to be this, that. So the frequency is just the speed of sound divided by lambda, and you are done.
Okay.
See, that's how simple things are. All right. And I can put on top of this one is if you keep walking, you will get to the next point. I mean, at point P, things are perfectly out of phase, right? But if you keep walking, it will just go, and then eventually another point, it's going to be in phase again. And when you get this point, let me call this point M. Then at this point, that means you are reaching the point where the delta R is perfectly one wavelength. So it's come back and in phase again. So that's the next maximum. And if you keep walking, of course, now you start to guess the progression over here. At point M, it's perfectly in phase. When you walk away from it further, it starts to get out of phase. Eventually, you might reach point N, and it's going to be the next minimum. And that delta R is going to be now 3 lambda over 2. You see what is going on next? If you keep walking, and then you will see the next maximum again. And if you keep walking, you get the next minimum, maximum, minimum, maximum. So this means if you keep walking up and up and up, you will see the alternation between, loud sound, quiet, loud, quiet, loud, quiet, on and on. Okay?
Okay.
All right. So that is it for today, guys. I hope you learned something today and not too bad. Okay. All right, guys, take care. And then I'll